So I threatened previously to talk about average value of a function. We're there. We're going to do it. So remember from single variable calculus that the average value of function of a single variable on an interval is going to be 1 over the length of that interval times the integral over that interval. Sorry, integral over the interval of f, right? And so most of the time when you're doing single variable calculus, you don't use set notation. So the length of the interval is written as b minus a, and the interval itself looks like the one from a to b, right? Okay. Well, we have exactly the parallel thing when we look at the average value of now a function of two variables on some region R. It's going to be 1 over the area of R, and then we're going to have the double integral now over R of f with respect to the area element. And later on, when we do triple integrals, we'll see that the average value of a function of three variables on some region R, now a three-dimensional region, is going to be 1 over the volume of R, and then we'll have the triple integral, and you can kind of guess what that means. I know we haven't talked about it yet. Triple integral over that region R of f with respect to the volume element. All right, so it's the same idea for all of these. You integrate the function over the region, whatever dimension it has, and then you divide by the measure of that region. And measure could mean length or area or volume, depending on what dimension you're in. All right, so how do we actually compute the area? So if we want to know what the area of the region R is, we can set it up as an integral, as the double integral of just the function 1 with respect to the area element. So what's going on here? Well, look at the following picture. If we have a rectangle of, and the rectangle has side length 1, then the area of the rectangle is equal to how long it is, right? So here we have that the rectangle has a side length of 4, so it's going to have an area of 4 square units. So what I'm saying is that with width 1, length is equal to area, which to anybody in the audience who does physics or engineering, you're going to say, wait, but length is in linear units and area is in square units, so that makes no sense. And okay, yeah, you're right. Yeah, you're totally right. This one here is in one kind of units, and this one here is going to be in some other kind of units. But the actual value is the same, so it can be computed one way or the other. This is exactly analogous to if you have some region in the plane. So here's the plane, here's my x-axis and my y-axis, and I look at the function which is the constant function equal to 1. So just let's go up by 1. So here we are. Then in this region underneath here, here, let's make it pretty. I bust out some highlighter effect. Okay, then the volume of this region here is going to be exactly the same as the area. So if the area of my weird blob shape right here has let's see, area is equal to 13, say, then the volume of the solid is also going to be 13. This time it's just going to be cubic units instead of square units, right? Okay, and so we can actually use this this idea right here in some interesting ways to switch things around. So, for example, suppose you needed to compute the the integral from 1 to e of natural log x dx. And you looked at it and go, oh god, if I do that straightforward, I might have to do some integration by parts, and it could be ugly. But I can interpret this graphically. Like, what is this saying? If you were in a Calc 1 class, they would tell you, oh, that's the area between the curve of the logarithm. So this is where y is equal to ln x. It's the area under the graph. Here, I'm in the mood for highlighters today, so I'm going to just talk about that region. This is like the first thing you learn about integrals ever, right? They give you the area under a curve. Okay, and then you can say, well, you know what it looks like? It actually looks to me like maybe we were first doing an integral in the dy direction, where we integrated from this one right here, y equals 0, up to this one right here, y equals natural log x. And then we did those slices from, I guess here's the first one at x equals 1, and then here's the last one at x equals e. So in other words, this integral is the same thing as the double integral of the function 1 dy dx, right? So, I mean, as seen from the side here, let me draw like my crummy attempt at drawing this in perspective. This is gonna suck. So we have, okay, so there's my logarithm. And so then I just went straight up to height 1. There we go. Okay, so what is the volume of that solid right there? Well, that's, you can see this is the same thing. Okay, and so it's just that the 1 is given by this double integral, and the first one looked like it was given by that single integral. So okay, so once I have figured out that I can understand the volume this way, then I can say, oh, well, I can do my old trick for how to convert double integrals from one way to the other. And now I want to think about it as if I'm integrating this way, right? So in this case, I'm going from this curve right here, starting there, and then ending here. But since I'm now integrating dx, I need to think about this as going from x equals this to x equals that. So this one over here, this green, this is x equals, and I go back to my formula right here and I solve that for x by taking the exponential of both sides. So apparently that's x equals e to the y. And then the one that I stop on is the vertical line x equals e. Right, so now I've got, I'm going from e to the y up to x equals e. Still the same integrand, 1, because remember the integrand never changes. And this time we're doing dx. And now I look for where I pick up those slices, and I've got my first slice going on right here at y equals 0. And then my last one right here, just nicking it at that point at y equals, and then I have to figure out where that is. But luckily I have the formula for figuring out what that is. Y equals log of e, so that's 1. So this is going to be the integral from 0 to 1 dy. And then that turns out to be much easier to integrate. So this is the integral from 0 to 1. And then evaluating the inside there, I have e minus e to the y dy. And then the exponential function is everybody's favorite one to integrate because it's really easy, nothing happens, right? So that gives us e times y from 0 to 1 minus, and then we have just e to the y from 0 to 1, and that gives us e times 1 minus 0 minus the second integral evaluated across is e minus 1 is 1. So there's our answer, and we were able to do it without integration by parts. If you try to do the original integral the way it was written, you'll see you have to do integration by parts, and it takes a bit more work.